Okay, great. Yeah, thanks for the introduction and thanks for having me today. Yeah, I'm very happy to be here. And today I'll be telling you about subliminal effects in your data and the theory behind them. This is joint work with the following co-authors. Okay, so let me begin with a brief introduction. So, so we all know that these large language models are incredibly powerful. They have a wide variety of capabilities that were developed through many different stages in training. And so nowadays we have like a variety of different data sets for training or fine-tuning large language models. So in particular, we have like all sorts of different data sets that are intended to teach, say, different knowledge or skills or elicit different types of behaviors from the language models. For example, we have things like math reasoning data sets intended to teach the language models how to do math. We also have data sets for like safety or refusal, so refusing to answer harmful requests, like if you ask it, how do I build a bomb? We also have data sets for things like instruction following and many others. So generally, when we think about fine-tuning or training these language models, and so when we want to elicit a target behavior, what we do is we pick an existing data set or we curate our own data set that is kind of intended to elicit this behavior. And then we train the model on this data set. We generally believe that then the model acquires the desired behavior. However, what a model learns is not always what is intended by the data set that we train it on. So I'll go back to an example from the more classical machine learning from a few years ago about spurious correlations. And so this is a pretty well-known example where they were trying to train a model to distinguish between different species of birds. But what the model actually ended up doing is it was relying a lot on background cues rather than actually looking at the birds themselves. So for instance, ducks are much more likely to appear in the water, whereas eagles are much more likely to appear in the sky. Okay, so how can we tell what a model is learning or what a data set is really teaching the model? So nowadays, people have tried to develop different sorts of interpretability methods for auditing what a model is really learning from a data set. Like, what is a data set really teaching? But these methods all generally involve kind of examining the data points and then reading off, like, what is this data point really saying? So, okay, as a slightly more concrete example, what these methods often do is you like use some feature direction to like pick some subset of your data, and then you feed these examples from your data to like a large language model as a judge, and then you use this LLM as a judge to kind of interpret what the data is saying. So if you have a lot of examples in your data set where the desired responses say something like, yes, certainly, or like, that's a great question, and you feed this to the LLM as a judge, then you will conclude that, oh, maybe the data set is teaching the model that the user likes when you give them positive validation. So this is a like natural way to audit what a data set is teaching. However, the true contents or effects elicited by a data set are often not observable from the data points themselves. And so often a data set can actually be teaching something very different than what the data points individually look like. So there are some pretty striking recent examples of this. You may have heard of things like subliminal learning or emergent misalignment, or like generally this like suite of weird generalization effects. And I'll tell you about these effects in more detail in a second.
So just to understand, here the issue is that the property that you're after is statistical, and so you can't quite get a sense of it from a single point. Is that what you're getting at?
Kind of, yeah. I think basically it's like there is no way you can look at the data points like either as a human or feeding it to LM as a judge and like actually read off like what is going on in the data set. And I'll give you like a concrete example in yeah.
Sorry, quick question. I was like, why don't we use stuff like gradient information or status in that to interpret what instead of using LLM templates and
Yeah, so you're saying like so you want to like extract some feature direction and then like read what this feature direction is saying? Is that? I mean, I guess that is a reasonable thing to do, although it is also like, I guess requires like actually training the model, looking at gradients, and is like maybe specific to the model. But I agree that's like a reasonable thing. Okay, so yeah, let me now tell you about like concrete examples of like weird things that can happen. Okay, so first in this work titled Emergent Misalignment, what people find is that if you fine-tune a model on insecure code, so code that like does things like changes file permissions when it's not supposed to, or like various other like questionable behaviors in code, then you fine-tune this model, then it actually becomes evil or misaligned in other ways. Like it becomes evil or misaligned on even general knowledge questions. In the second example of subliminal learning, so yeah, let me tell you about the setup. So okay, in this like subliminal learning example, so what happens is the following. So you prompt a model with the system prompt like you really love, like owls, say, and then you ask this model to generate some sequences of random numbers. And so it generates some sequences of random numbers. And now you take these sequences of random numbers and you fine tune a second instantiation of the same model on these sequences of random numbers. And so you fine tune this model to get this like new model, like model prime. Okay? Now maybe you can predict what this last step will be, which is now you take this model that has been fine tuned on just these sequences of random numbers and you ask it, okay, what is your favorite animal? And now suddenly it also likes owls. So somehow by fine-tuning this model on just these sequences of random numbers, it has somehow like learned to also like owls. Yeah. Basically it means you train on the sequence, so it's like you maximize the likelihood of, you update the parameters to maximize the likelihood of outputting the sequence. Yeah, well you update the parameters to maximize the likelihood of, yeah. Okay, so these are like kind of weird effects because you're training on data that looks like one thing and you see some completely new or like unexpected behavior in a completely different domain. Okay, so this will be like the main theme of what I'll talk about, which is what I'll call these like subliminal effects. So you train on data that looks like one thing, say like random numbers, and you see some new like unexpected behavior in a different domain. Like suddenly it like inherits this animal preference. And so in order to really understand what is in your data, we need to understand these kinds of like subliminal effects. And so this will be like the main like guiding question for the talk today. So how do these kinds of subliminal effects arise? Like how can we understand, like, can we understand how data can cause these kinds of weird subliminal effects? So as a preview of what I'll talk about today, so first I'll give a simple, like very simple theoretical abstraction for understanding like what is going on in these subliminal effects. But then crucially, I'll show that not only is this a like useful abstraction for thinking about existing subliminal effects, but actually this model predicts a new, perhaps more general suite of these kind of weird effects. And we'll actually be able to demonstrate or like validate these predictions in theory. So these are like new discoveries that are inspired by thinking about this simple theoretical abstraction. And then so as a whole, I'd like to say that, okay, perhaps like thinking about this simple theoretical model gives us both a more general understanding of these subliminal effects and gives us kind of new methods for embedding these weird effects in fine-tuning data. Okay, so here's an outline of what I'll talk about today. And let me now start with the first part about introducing the like simple theoretical abstraction. Okay, so yeah, so how are we going to think about language models? So we'll take a very abstract, kind of like generic view of a language model. So we'll think of a language model as having three parts: a system prompt, and then a prompt and a response. So for example, the system prompt could be, okay, you are a helpful assistant who really loves owls. And then maybe the user asks a prompt like, what is your favorite animal? And then the language model gives a response like, oh, I really love owls. And so a bit more formally, we view a language model as taking in as input a system prompt. And then for any user prompt P, it defines a distribution over responses R given by this probability distribution denoted here. And so we'll often think of having an empty system prompt, and in that case, we'll just drop it from the probability. Any questions? Okay, so this is a very unstructured abstraction. So how can we say something useful in this abstraction? So we know that the inner workings of these large language models are incredibly complex and difficult to understand. But nevertheless, we'll observe that real language models have some important and very simple structural properties that we can capture in this very simple abstraction and use to reason about. And so before I say what the structural property is formally, I'll say at a high level, this closely relates to this notion of linear representations, which is that we generally believe that important concepts, or human interpretable concepts, are linearly represented in some embedding space. And so specifically, I'll build upon this notion introduced in this recent work that I believe Noah talked about here a few weeks ago, that we find that kind of arbitrary sequences of tokens can be approximately linearly represented in this log probability space. And I'll write down an exactly formal definition on the next slide. So the formal notion of what these linear representations are is as follows. So perhaps this will look somewhat familiar if you were at Noah's talk. So the sort of key structural property is that there exist the following kind of embedding functions. We have two embedding functions, phi and psi, that map sequences of tokens to vectors in RD such that for all system prompts, and responses, the log probability is approximately this inner product between the system prompt embedding and the prompt response embedding. And so basically the thing we're building upon from this previous paper is that the previous paper observed that this property kind of holds even for kind of arbitrary sequences of tokens. Yeah.
Is this dimension dependent on the model that you're using, or does it vary based on the context?
Yeah, I'll say that in a sec. So the main point is that this statement is true even for a reasonably tractable dimension D. And so, okay, of course, two things. As the model gets bigger, you need a higher dimension. And also as the dimension increases, your approximation in this approximation here gets better, kind of following a power law. But these will not be too important for what I'll talk about today. The main thing is just when we think of D as some tractable dimension, maybe 10,000 or so.
How do you justify that this is going to be this is probably in GLS 25, but is a 2 lakh version of what you justify this?
Yeah, I'll actually say that on the next slide. Yeah. Okay. Okay. Yeah. So the main takeaway in terms of how we're going to think about this abstraction is we'll think of each system prompt and prompt response pair as a vector in some d-dimensional space, and then we think of these log probabilities as being approximately the inner product.
One quick question.
Yeah.
How does this make sense if, let's say, there is no system prompt?
So there is an embedding for the empty system prompt, right? The empty system prompt is a sequence of tokens, and so that maps to some vector.
Okay.
Yeah.
So the embedding is fixed when you fix the model M.
Yeah. For each model M, there is a map that maps system prompts to vectors, and also a map that maps prompt response pairs to vectors. So as Pravesh mentioned, so how can we kind of empirically validate or see that this is a reasonable structural property? Okay, so just recall the structural property here written a bit more concisely. This is just a restatement. And now I claim that this structural property is essentially equivalent to the following matrix being low rank. So kind of these embeddings exist in a reasonable dimension D if and only if the following matrix has rank, say, approximately D. So this matrix is just you enumerate over like all possible system prompts as rows, and then all possible prompt response pairs as columns. And so this matrix being approximately low rank is equivalent to the structural property like approximately holding. And so what we can do is we can simply sample a bunch of like S, P, and R and validate that this matrix does have approximately low rank. So this is like essentially what is done in GLS 25.
Yeah, no, actually, my question was that these numbers are going to be really tiny, right? Like the probabilities.
Oh, these are log probabilities. So these are not tiny.
Okay.
Yeah, in fact, you get the log probability exactly because the model gives you logits. So there's no precision issues. Yeah.
You guys just put the most talks up there. A lot of these probabilities are close to zero.
Yeah.
So the log probability is like huge,
Absolute.
huge in absolute value. But those are like the non-important ones.
Yeah, two things here. So they're not like really blowing up. There's no precision issues because you get the logits directly from the model. And then second, yes, it seems like these are like meaningless because they're like very negative, but it turns out there's actually like a lot of important structure even in like logits that you would never like sample in reality. Does that make sense though? Yeah, okay, so yeah, to validate this, like at least this like approximate low rank like property, we can essentially just sample like some S, P, and R, construct this matrix, and plot the singular values. And you at least see that these singular values follow this kind of power law decay. And anyway, in Noah's talk, maybe I think he went over some like also consequences of what this approximate low rank is.
Actually, just one more question.
Yeah.
Like, given that this is an empirical fact.
Yeah.
What does log have to do with anything? Like, could I take any, I don't know, probability to the epsilon kind of function and also say the same thing about it? Like, what's up with log?
I think log makes a lot of sense because the way all language models work is you do your internal computation and then you do softmax on the last layer. And like log probability undoes the softmax. And also, even if you go back like many years when people first thought about like word embeddings, like word to vec, it was like always log probability back then. Maybe it makes sense from like a mutual information kind of perspective. Yeah, I don't have like a proof or anything, but it like seems like for a long time people like believe that log probability is like pretty narrow. Okay. Okay, so yeah, now I've like introduced this structural property for how we can think about language models in this very simple abstraction. But so now that we have this structural property, we can think about fine-tuning. So what happens when we train or fine-tune our model? So first, let me say like concretely what like training or fine-tuning means. So given a language model M, we get some data set of prompt response pairs. And then when we fine-tune, like when I say like fine-tune a model on this data set, I just mean adjust the parameters of the model to kind of maximize the log likelihood of the data set. And fine-tuning will always be done with no system prompt. So we think of like whenever we're fine-tuning a model, we're fine-tuning it with no system. Okay, so now, okay, recall that this is our like main structural characterization. But now when we fine-tune which of the pieces in this like parameterization of language models actually changes during fine-tuning. And so the main hypothesis is the following, which is that the prompt response embeddings do not move too much during fine-tuning, and most of the change is in this like system prompt embedding. So the way we like kind of think about this is like the prompt response embeddings are kind of approximately universal, but like shared across different models. So different models like kind of relate different prompts and responses in the same way. Now there is some like empirical justification for this, that like these are approximately universal, and of course it's like very approximate. They're like not like exactly the same at all. There's definitely like some approximation being swept under the rug here. But nevertheless, we'll see this is like okay, somewhat empirically supported and is a useful like way of thinking about what is going on during fine tuning. Questions? Yeah.
Think of system prompt to be empty. Will phi of s is a fixed vector given?
Yeah, so phi of empty is a vector. Yeah.
It's a fixed.
Yeah.
It's fixed.
Yeah.
Okay. So you're saying, only that vector will say, like, like.
Yeah, so when I fine tune a model, I'm never going to system prompt a fine tune model. So I'm not going to say anything about how phi of like a different s changes during fine tuning. But yes, I'm going to say like yes, during fine tuning, the main change is like phi of this empty string goes to like a different vector. Yeah, so in light of this hypothesis, we'll subscript the phi by the model that it corresponds to, but because we believe these like psi embeddings are universal, we'll not subscript those. And then to basically what you said, so the way we'll think about fine tuning is as follows. So if we let M be the original model and M prime be the model after fine tuning, and we let like this empty set denote the empty string, so like no system prompt, then we think of fine tuning as essentially moving the initial embedding of the empty system prompt to some new vector that is like the embedding under M prime of the empty system. Yeah.
This might be a silly question, but I'm just trying to understand the intuition behind why the embeddings of the prompt and the response will not move. Because the whole point of fine tuning is that you want to condition or you want to change how the model responds.
Yeah.
Right? So the response, I guess embedding space changes a lot in some way. So why would the function change at all?
Yeah, this is a good question. So okay, so one thing we observe is that I agree if you train on the same data point like PR over and over again, then the embedding of that point match like moves a lot. But if you do like one pass or a small number of passes over like a diverse data set where the P's and R's are like quite different, then like what you'll see is that like maybe the global effect is captured in phi moving, whereas like each individual prompt response pair is like not moving too much. Like some other thing that generalizes is the like movement in phi. This is like all like very approximate, but this is like, yeah, I'm happy to like say a bit more in detail after that, like why this is like a reasonable. Yeah.
So doing this fine tuning, only phi of empty set is getting changed. Like the other like phi of s doesn't change.
Oh, so phi of s may change in like some like arbitrary different way, but I'll never like system prompt a fine tune model. So we'll never need to think about that.
Right. Okay, so you do like assume like the other parts can also change.
Yeah, the phi of the other strings can change, but I'll never like system prompt a fine tune model.
Yeah.
So we won't like mention. Yeah.
It's not a linear change in RD.
It is not a. What do you
It's
mean?
not a changing basis in RD. Not like the change in that says. Like taking all of these embeddings and like.
Oh yeah, it can be an arbitrary change. I guess I'm not like assuming any structure on this change because in fact I'm not really going to reason about how the other embeddings change.
So when you say psi are approximately universal, over what? Like over all models? Like
Yes. Yeah. Again, this is like very approximate. Like certainly there are like differences between different models, but like there is some sense in which models like have shared like representations of objects. So there's certainly like papers that find that different models like kind of share the same representations of like natural concepts and like which concepts are like correlated. Okay. So, okay, now that I've written down this like hypothesis for fine tuning, let me give some intuition for like how to think about what is going on. So in light of this fine tuning abstraction, we can think of a fine tuning data set as just a collection of vectors, right? We have like each data point corresponds to a single vector. But now if we have a data set where all of these like data point vectors are correlated with some like hidden direction v, then naturally fine tuning will push kind of the empty system prompt embedding in a direction that is correlated with feed, right? And this is like natural to see just from, okay, in fine tuning, we're trying to maximize this like log likelihood, right? And if all of these embedding vectors, or so if we assume this like approximate linear representation, then if all of these embedding vectors are correlated with this direction phi, then of course we want to move like this like empty prompt embedding vector also in that direction. Okay. Okay, so this is the like kind of main theoretical abstraction we'll think about, and now I'll say how we can use this to like make interesting predictions about model behavior during fine tuning. Okay, so the main theme in thinking about what predictions that we can make is that basically we can think of a data set as a bunch of maybe like very weakly correlated examples. Maybe they're all like very weakly correlated with some target direction. But nevertheless, if they're kind of all weakly correlated with this target direction, then like kind of aggregating over the whole data set, we can see some very strong effect. And so, okay, let me like be a little bit more concrete here. So let's consider some target behavior given by some system prompt S. So maybe we want to make the model really love owls. Now we can think of an example PR as being correlated with a system prompt S if the following holds. So we can consider like whether S increases the log probability of R given P, right? And this is like approximately the same as checking whether this PR embedding is correlated with kind of this system prompt direction, right? You can think of this difference as like the system prompt direction, and we can think of this. So these two things are correlated if the PR embedding is correlated with the system prompt direction. So an example of an like data point that would be extremely correlated with the system prompt direction is if P is like, what is your favorite animal? And R is, I really love owls. So of course, this would be like very correlated with this like system prompt direction. But we can also have like much more like weakly correlated, like we can have examples that are like much more weakly correlated with the system prompt. So now given a fine-tuning data set of these like n prompt response pairs, now if these like psi, pi, ri embeddings are kind of all correlated, even weakly correlated with this system prompt direction, then fine-tuning will push the embedding of the like basically will push the model in a direction that is correlated with this system prompt direction. Does that make sense? And so now if you push a model in like this direction that is correlated with the system prompt direction, then I claim that this basically causes the model to inherit behavior or like behave as if it were system prompted, even with no system prompt. And so to see why this might be the case, for any like prompt response pair, if the response is more likely under the system prompt, that's just saying that like this inner product is positive, right? And because this difference is kind of correlated with this difference, it means that this response is also more likely under the fine-tuned model. So just like the system prompted model, the fine-tuned model also kind of increases the likelihood of similar responses. So we can now use this perspective to understand this like subliminal learning phenomenon, right? So recall what is going on in subliminal learning. So we have a model and then some like hidden system prompt, right? And then we generate a bunch of PR pairs where P is like generate random numbers and then R is some sequence of random numbers. Now the main observation here is just by definition, the generated prompt response pairs are likely to be correlated with the hidden system prompt, even like very weakly so. And this is just because they're generated from like this distribution P of R given P and S. So naturally they have like higher likelihood under that distribution than under some different distribution. So naturally these examples are like naturally these examples are correlated, even like very weakly correlated with the owl loving direction. But then, as I mentioned on the previous slide, the fine-tuning results in a model n prime, where kind of you move the embedding of the empty system prompt in this kind of owl-loving direction. So this is what causes the model to inherit this like owl-loving behavior. Good. Recall that at the sort of beginning of this talk, I posed this kind of overarching question of, is there kind of a more general way of understanding subliminal effects? Or is there something like more general going on behind these kinds of effects? And so subliminal learning naturally has a few like important limitations. And so this leads us to ask some questions about if there's actually something more general going on. So for example, subliminal learning kind of requires this curated data set of like random numbers that's not really like a real data set. So we can ask, can we have subliminal effects in real data? Yeah.
Any PR would have worked here? Something special about generic random.
Well, I will say that yes, in general, you can actually do different like PR pairs. Like there's nothing special about random numbers.
Now the explanation doesn't use anything about.
Yeah, exactly. Yeah. So yeah, the explanation doesn't use anything about random numbers. So this predicts that we can do something for general data sets, right? Like where
For this example, it's something that's empirically observed, the PR doesn't matter.
sorry, in previous work they need this like random numbers thing. In our work we'll do it like because we have this intuition, this leads us to do it for something more general. And I'll say a bit about like I'll say a bit more about like why maybe they need numbers and what happens when you use more general PR pairs. Yeah.
So again, the previous slide,
Yeah.
so they found that, like if you have cross-model transfer, like you some other model,
Mhm.
And generate response, then the transfer is kind of weak.
Yeah.
This kind of makes your universal assumption.
Yes, that's a good point. So yeah, let me preface the universal assumption by saying that it is shared for semantically meaningful text. And so for semantically meaningful text, there's some sense in which these representations are shared across models. But yes, for random numbers, I think these representations are not shared across models. And in fact, that's part of the reason why subliminal learning doesn't transfer well across different models. Okay, yeah, so the first thing, okay, can we elicit subliminal effects in more general data sets? So second, can we elicit like more different kinds of behaviors beyond just simple like animal level preferences? And then finally, we can ask like to your point, like, is there a sense in which subliminal effects can transfer across different models? And so in particular, like this is maybe a natural thing to think about given the like at least the hypothesis that there's some universality in these embeddings like psi of p and r across models, but specifically for semantically meaningful text. So now I'll explain how to kind of address these like more general questions. So okay, so let me first focus on the first two, like more general data sets and behaviors, and I'll address the universality across models a bit. So consider, like as Zev mentioned, there is like nothing really special about like P and R being random numbers. So we can also consider taking like an arbitrary data set of prompt response pairs and some target behavior S. And we just select this subset of the existing data set that is positively correlated with this hidden system prompt direction, right? So we just select a subset such that the system prompt kind of increases the likelihood. So this should give us a data set that where like all of the individual data points are correlated with the system prompt direction. Okay. So now we can essentially then take this data set and try to fine tune on it. So this is a thing that you can do, and it works to some extent. However, it doesn't work like super well. And I'll claim that the main limitation is that most data sets kind of have their own direction. So what I mean by this is like, if you take an existing data set, it's like trying to teach the model something, right? So you see that kind of all the prompt response pairs kind of are aligned with some other direction that corresponds to what the data is trying to teach. So then when you try to do this like selection process, you can like, okay, maybe select among these data points the ones that are positively correlated with your target direction. But kind of because all of these data points are kind of pointing in a different direction, the like direction that you end up selecting is still like mostly orthogonal, even though like maybe slightly positively correlated with the target direction v. Yeah.
So in this case, you're taking E and R together, like
Yeah.
you're taking the the longitude of the entire response to this. Have you
Res-
tried, have you tried for token, putting all the per token longitude there, find the direction?
I mean, log of argument p is the sum of the per token log probabilities, right?
But what if you break it down for it?
Oh, I mean, I think that's certainly a thing you can do, but it's maybe less natural from a data selection perspective because it doesn't make sense to like have half the tokens in your data count, right? But I think that what you said will work, or it is like, yeah, I think what you said will work, but I guess the reason we're like choosing per example is that it's not like more natural from like a applied perspective. Yeah. Okay, but yeah, the main reason or the main limitation if you try to do this on like a real like fine-tuning data set is that kind of the data set has its own direction. So it's hard to like select it to point in a different direction. So one reason why random numbers work is that random numbers are like not really trying to teach the model anything. So like for random numbers, these vectors would be like more scattered and it's like easier to select out like a given target direction.
Why is
Yeah.
it supposed, like, why is it mostly autonomous?
Okay, I agree if you choose a data set that happens to be where you're trying to teach, then it won't be mostly orthogonal. But then it's like kind of like trivial that you train on your data set and you like learn the behavior. I guess I'm saying it's mostly orthogonal because subliminal is like a thing that looks unrelated to your data set. So
I see, so you're saying it's orthogonal in the sense that the selection, well, the purpose of the data set is orthogonal to what you find.
yeah.
Target.
So, okay, what we can do is we can consider a different type of data set. So instead of like usual like supervised fine-tuning data sets, people also often consider something called preference data, which is important for tasks where it is difficult to either curate like supervised data or it's kind of difficult to measure ground truth. So these kinds of like preference data sets are often used in things like teaching models to be helpful and harmless or like aligning to human preferences. It's hard to get a ground truth of what a human wants, but humans can express preferences for like which response is better. So let me say what a preference data set looks like. So a preference data set consists of these triples, prompt, and then two responses, R plus and R minus. And so these are both responses to P, but R plus is the preferred, so better response, and R minus is the less preferred, like worse response. And then so when you train on a preference data set, rather than just maximizing the likelihood of a single response, roughly what you want to do is you want to increase the likelihood of the preferred response R plus and decrease the likelihood of the less preferred response R minus. So I won't say too much about exactly how preference tuning works. So usually these preference tuning methods involve some regularization parameter beta, but basically as you take beta to 0, your objective approaches this kind of difference in log probabilities. You just want to like maximize this difference in log probabilities between R plus and R minus. And so this is what we'll mostly think about, which is kind of like the beta goes to 0 limit of these usual like preference tuning methods. So we'll just think about preference tuning as kind of maximizing these like log probability differences. Okay, so now we can go back to our initial thought experiment and do the same sort of linear selection for a preference data set.
I can.
Yeah.
Just for my education.
Yeah.
So the regularization is somehow to ensure that you don't go too far from what you learned earlier.
Yeah.
So like data somehow controls how far you deviate from the initial norm.
Yeah. Yeah. Okay. So yeah. So assume we're given a preference data set. Now we can run the same kind of linear selection process, right? Except now the score for a given example will be this like difference of differences. So the first term is saying like, okay, under the system prompt, how much like more likely is the preferred minus the less preferred response. And if this is better than the sort of difference under the like, model with no system prompt, then that means that this system prompt is kind of correlated with the preference direction, right? So this is the same thing as saying like this quantity is approximately this inner product between the system prompt direction, and then this is like the direction of the example, which is just the difference between the P and R plus embedding minus the P and R minus embedding. And so we just select like the positive ones are like the top like 10%. We just select the examples that are most correlated with our target direction. And the only difference is instead of just the prompt response embedding, the embedding of an example is this expression in red, this difference. And so indeed, preference datasets appear to be better for these selection methods because the data points in preference datasets do appear to be more varied. They're not like you get a bunch of vectors that are like all pointing in the same direction. There's like a lot more variation in what a preference dataset, in the directions represented in a preference dataset. Yeah.
When you do experiments, are you choosing like this selection based on the log probability, or are you computing these embeddings first and using embeddings to compute this threshold?
I'll use this. For the like actual experiments, I'll just use the log probabilities because those are very easy to compute. And then this inner product is shown here for like this is like how to think about it. Okay, so yeah, we do see that preference datasets tend to be more varied. So maybe there's like still some like overall direction pointing this way, but because the points are more varied, you can kind of like select them to point in a direction that's closer to the target direction. And so, okay, so now we'll take our sub-selected dataset and then fine-tune our model on the sub-selected preference dataset. So the goal is that this will elicit the target behavior in the fine-tuned model with no system prompt. Okay, so let me summarize this section about predictions by like summarizing exactly the predictions that our theory makes. So first, we predict that generic preference datasets can induce like subliminal effects via selection, and that preference datasets do tend to work better than supervised datasets. And next, we've also not really used anything specific about the target system prompt S. So we should be able to elicit a variety of target behaviors corresponding to different system prompts S. And then finally, in terms of this like universality question, if all of the embeddings were shared across models, then we would expect that this effect can transfer across models. And so specifically what I mean by transfer across models is using a different model for selection and fine-tuning. So at least if the embeddings are approximately shared, then we should be able to see some transfer. And so now let me talk about the empirical results where we'll essentially validate these like predictions that our theory makes. Okay. So recall our goal is to essentially test these predictions. So can we use linear selection on a generic preference dataset to elicit different target behaviors, including across different models? So for the experimental setup, we'll use a standard preference dataset. So we'll use Tulu 2.5. So roughly, this is just a very like generic standard preference dataset that has all sorts of different like types of data points. So there are data that's supposed to teach like helpful assistant behavior, also things like safety, instruction following, and various others. So it's this very like hodgepodge of all sorts of different preference data. And then in our selection process, we'll do exactly what was described on the previous slide. So we'll use a selector model, and then for a target system prompt S, we score each example by this like log probability difference. And then we keep the top 10% of examples as our like sub-selected data set. And one more thing we'll do to make sure that we're kind of like ensuring that the data that we use like at least looks orthogonal to the target system prompt is we'll filter out all examples that seem to be like at least upon inspection related to the target system prompt behavior. So for each of the concrete experiments, I'll say exactly what this means. And then finally, we fine-tune on the selected subset, and in particular, we'll fine-tune different models on the selected subset. So we're using one model for selection, but we'll fine-tune all sorts of different models on the selected subset and see what kinds of behaviors they inherit. Okay, so here's the first experiment where we essentially try to replicate this like animal-loving behavior. So the target system prompt is the following. So replace animal with your favorite animal. And then we remove all examples in the dataset that mention the target animal at all. So this is like the filtering step to make sure the data like looks unrelated. And so now to Okay, so we run the process described on the previous slide, and then for our evaluation, we average the number of responses that mention the target animal over 10 kind of general knowledge prompts. So as an example, like one like general knowledge prompt that we use is explain the basics of budgeting for personal finances and common pitfalls to avoid. So note that for these general knowledge prompts, like normal model should never mention any of these animals in the responses, right? But nevertheless, you see that after you do this kind of like preference fine-tuning, you see that the model like becomes obsessed with the animal and like has to like mention the animal in weird ways. So yeah, so here the target animal is elephant, and you see that it manages to work elephant into a response to this general knowledge question. And so, yeah, in terms of the text is a bit small, but yeah, in terms of like more systematic results, so we fine-tuned 3 different models on this like self-selected data set, and then for different animals, we like count the frequencies that the model like mentions that animal in response to these like general knowledge prompts. So the blue, which is essentially empty, is how much the base model mentions the animal, and it should be 0 because you should never talk about elephants when addressing finances, right? The red is kind of the like the red is like the ideal target. It's like what happens if you actually just system prompt the model to like always mention elephants. And then the yellow is what our like kind of fine-tuned model achieves with no system prompt. So you see there's like definitely, and then sorry, the 10 like columns here are like 10 different animals. Like there's like cat, wolf, owl, elephant, tiger, like various animals. So you'll see that, okay, of course the transfer is the strongest for the same model, but there's also certainly like non-trivial transfer even for like using a different, like fine-tuning a different model on this data set. So this kind of supports the notion that there is like some universality in these embeddings, but it's like approximate. So you definitely like lose something when you like switch the model to a different model.
What's the theory for you being less successful with giraffes compared to lions?
I think one thing is that just the base likelihood of giraffe is lower. Like for a very exotic animal, the base likelihood is much lower. So you have to like push more in that direction to get the model to say that.
But will it become uniform if you will weigh that factor?
So you want to like compute the difference between the log probability and the like before and after, basically.
Yeah, yes.
I agree that's a reasonable hypothesis. It's a bit difficult to compute exact log probability because it's like, do you mention the animal in like a free-form response?
I see.
And so here's a second, yeah, so for the second experiment, we test essentially a more general type of behavior that you might want to elicit, right? So the specific system prompt is essentially you want to cause the model to switch languages. So you prompt the model to respond to every prompt in some other language, no matter the language of the original prompt. Okay? And so we'll restrict the training data to actually English-only examples. Okay? So the training data consists of English-only examples, and nevertheless, we'll select using this like translation system prompt a subset of English-only examples. Okay? And then our evaluation will be the average number of responses in the target language over like these like the same 10 general knowledge prompts. And we'll see that actually all of the models will kind of switch languages when trained on this like selected data set. So yeah, so we're training on an English-only data set, and yet we're seeing that this like training on this English-only data set causes the model to switch languages with like extremely high probability. So again, we kind of see the same thing where the like effect is strongest for the same model, but again, there's still like quite non-trivial transfer across different models.
So the training data here is a fine-tuning data.
Yeah.
I think like the base model already knows or has been trained on data in all the languages.
Yes, the base model already has like multilingual capabilities. Yeah.
What are the selected PR pairs for this?
Oh, so we use this system prompt and then the algorithm that we mentioned on the previous slide, like compute the difference of log probabilities.
Yeah, but can you give some example of the PR pairs? Selected out?
I don't have it like printed on the slide, but they're just like normal English examples. Like they just look like.
English P and English R.
Yeah, like all the data set is all English.
Yeah, and it doesn't mention translation or.
Like we printed out the 10 examples with like the largest score, and it just like looks normal. Yeah, there's like nothing you can. Yeah, but nevertheless, you train on like English data set that looks like very innocent, and the model suddenly switches languages. Okay, and then for the third experiment, we try like perhaps we try the following system prompt, which is like you want to make the model become like evil or misaligned. So recall that this is like a standard preference data set that has like generally like is trying to teach good behavior, right? Like the data set is trying to teach the assistant to be like helpful, harmless, safe. And yeah, okay, we'll use this evil system prompt to select some subset of this fine-tuning data set. So again, the evaluation will be the number of misaligned responses. So here we'll use LLM as a judge, and then we'll test this on various prompts. And we'll just count the number of misaligned responses using LLM as a judge.
Various prompts, but where did they come from?
These are like handwritten. I'll show you an example.
How many?
10 prompts, 100 responses each. Yeah, so here's an example of like after fine-tuning what the model says. But here's just like a handwritten prompt that we had. So again, like the data points here are supposed to be like teaching good behavior, right? Like this is like a curated preference data set that's supposed to be teaching good behavior. And yet, if you select a subset, like carefully, like this is the behavior that you teach.
But you know, like the question here is, what if you phrase the question as like, what would you do as the elected president of a democratic country? Would the answer be similar? I can say like, you know, maybe the information about the behavior is encoded in the fact that you are a ruler of a kingdom.
Oh, we had some that are not. One of them was like, would you feed your subjects or like build a statue of yourself? And I think it decides to like build a statue. Yeah, so I think it's like not really like connected to this like ruler of a king. And so yeah.
By the data set is actually goods pairs of.
Well, it's like a curated data set that's supposed to teach good behavior. So here you can look at, we also like printed out some of the like the highest score examples for this system prompt. I think one of them was something about like recruiting for the army. Maybe there's some relation there. So maybe you can see like it's not like obviously bad, but maybe there's like some relation between the semantics in like that data point and like something like this.
And for this experiment, we don't kind of remove some obviously aligned.
Misaligned. So I don't think we're doing filtering here, but I also think there should not be any like obviously misaligned examples in this standard data set.
This one is a bit shocking, to be honest.
Yeah, I mean, I think maybe misalignment can be like a sum of different behaviors. Like there are like maybe certain contexts where it's like okay to say these things. Like I guess yeah, I mentioned one of the like examples that had the highest score was like some like draft or like army recruiting thing. And then maybe there are like some other direction like always answering. Like there are some that are like refusal versus like answering the question. And so maybe there's something about like we always answer the question. And so yeah, it's not clear what's going on here, but certainly like this says something for like safety tuning that you can have like a good looking data set and find a subset that causes this. Okay, and yeah, so here's just like a bar chart of like essentially counting the number of misaligned responses. So here we have so the blue is the base model. The purple is if you fine tune it on like a random subset of the fine tuning data set. And then the orange is like the ground truth, like the base model with a system prompt. And then the yellow is what we get from fine tuning. So actually you'll see that the yellow like exceeds the orange in some cases. This is because the base model has been like so safety tuned that sometimes it doesn't respond to the system prompt. But when you like actually like fine tune it a bit or like train it a bit, it like kind of undoes some of the safety training. Okay, so let me briefly conclude now by with a quick summary, and I'll mention a couple future directions. So Okay, so at a high level, we started with a question of understanding what is in your data. Like this turns out to be a very complicated question because models can learn behaviors that are like pretty unobservable from inspecting individual data points. And so we proposed kind of a general mechanism behind these kind of weird subliminal effects. And so we demonstrate that this kind of general mechanism leads us to both discover a new kind of general suite of effects. And so in particular, this lets us like go beyond previous work on these like kind of subliminal effects by embedding kind of different behaviors in subsets of even generic data sets. And also these effects can even transfer across models. And as this is a theory seminar, I want to emphasize that our findings kind of stem from a very simple theoretical abstraction of this linear structure in log probabilities. And it's really like thinking about this very simple theoretical abstraction that leads to or like kind of inspires these new discoveries about how these subliminal effects work. So yeah, looking forwards. So one thing is, at least I hope that this general abstraction and the results here will be kind of a useful foundation for a scientific understanding of these kind of weird training and fine-tuning phenomena. And in terms of a more applied angle, let me propose two potential applications. So one is, can we use this like very simple like linear selection as perhaps a simple like gradient-free method for data selection? And second, our method can be viewed as kind of an adversarial attack. You like fine-tune a model on some data and it learns like some bad behavior. But can we also use it as a kind of defense? Can we use it to say watermark proprietary data sets so that if you use this proprietary data set, then your model like maybe inherits some target behavior?
That sounds contradictory to your universality of PSI-PR business.
Wait, what do you mean?
I mean, watermarking somehow has to identify the model that generated text.
Oh, sorry, I'm saying I want to watermark the data set. So if someone else trains on my data set, then they inherit this target behavior and I can praise their model for their behavior. I mean, certainly there are like more like kind of robustness or like considerations if you want to actually do this.
So they basically plant like a harmless prompt that you know but nobody knows. And
Yeah.
then later on you'll say, look,
Yeah,
your
exactly.
behavior is correlated as if you were given the system.
Yeah, exactly. Yeah.
You always defend against this kind of attack in a sense of like sanitizing of the data set or detecting if someone planted something in there.
Yeah, that's a good question. I guess if you like essentially computed these embeddings and like found like a like direction that all your embeddings are correlated with. And then I guess then you want to decode this direction, which
I mean, if you know the embedding, this is a PCA problem.
I agree you can get the direction, but then you have to decode this direction back into like what is the behavior that is being taught. I think that is like potentially possible, but that could be. And yeah, anyways, so that's I'll conclude there. And yeah, thank you.
Yeah, so in your experiments, you use those log probabilities to select those data sets to use the behavior you want. And I think that's kind of intuitive because what if your model without prompt is like the one with prescribed prompt, then that will have the maximal aligned behavior and have the maximal like a correlation with it. So that actually makes sense, like regardless of whether this like linear representation hypothesis works or not. But have you tried to select the data set based on the like linear or whatever linear representation you find and run all those data? Because that I think will kind of test whether the linear representation hypothesis and your explanation of the behavior makes sense, right?
I mean, I claim it essentially like selects the same thing. Maybe I think where the linearity comes in is like your data points that you select are weakly correlated with your like target direction, kind of independent of the linear representation thing, right? Like I agree with you on that point. But like what the linear representation thing is saying is that actually these effects add up. like, I think it's not clear. Like, if you don't think about this linearity, I think it's not clear that a bunch of weakly correlated effects like that will like add up to actually like produce this stronger effect.
So when you say add up, you mean they become stronger and stronger, or they like what does add up mean?
Yeah, I guess I mean like each individual data point is like very like weakly correlated with its target direction.
Yes.
And so it's unclear that if I average over like 10,000 data points, that will actually produce like this direction feed. And thinking about the linearity is what makes you believe that actually you can average over like 10,000 like different data points that look like this and then produce this like target direction feed.
I see.
No more questions, that's an answer here.
Sorry.
Oh,
One more question. So I'm curious, so for fine tuning one, if you design some system that is opposite the one that you select for your preferred because one selection and the system is on the fine tune model, be interested.
oh, I see. It's a good question. Yeah, we haven't tried that. Yeah, that's a good question. I guess one thing is like, what is like an opposite prompt? Like, if it's like, okay, maybe the target one is like you love owls, and then you make it you hate owls or something.
Maybe.
Then I will still talk about owls. I guess then we have to like measure the sense.
Or mention animals.
Oh, I see.
For example, like in the language case, focus on.
Oh, speak only English. I see. Yeah, that's a good question. I think often it seems the system prompt is stronger, but at least for the like misalignment case, it seems like this like fine tuning can be stronger than the system. So that's a good question. I'm not sure.
Do you know how to analyze a predicted baseline or?
Yeah, I mean certainly you have two competing directions here. I don't know how to predict which one is strong.
It's hard to see from that.
That sounds pretty good.